Hello everyone. In this video, I will explain the noise theory. Let me explain what is this noise. Noise is an unwanted electrical signal which is available in our communication system so that we will observe some disturbance in our system. This disturbance may be in audio, sometimes it may be in the form of video. In analog communications, we generally see disturbance either in audio form or else in video form. If you are listening in an FM, sometimes you are going to observe breaking of the voice signal. That you may consider it as noise. While watching the TV, sometimes you are going to see there will be an overlap of other channel or else the skipping of picture is happening. Even that is also comes under disturbance in your signal. That's why we call that one as noise. In digital communications, this disturbance we will represent it as error. While defining the noise, I told you it is an unwanted electrical signal. Why I am using this term electrical signal? The reason behind that is all the communication systems that we are developing are electrical based. If you design a mic and a speaker, it works with the principle of electrical quantities. If you design a mobile, it works with the principle of electrical signals. Any unwanted signal, especially electrical signal, that disturbances your communication system, we define it as noise. Before going into the further topics on noise, let us see how we categorize this noise. Noise is categorized into two parts. One is correlated noise and uncorrelated noise. Now, correlated noise, let us say you are listening in FM. While you are hearing, if you see any type of disturbance other than the voice signal from the transmitter, you call it as correlated noise. That means when the signal is present and if you observe any noise there, that means your input signal for your FM receiver is signal as well as noise. And the noise which is developed here is having a relation with the signal. That's why we call this type of noise as correlated noise. That means in correlated noise, we have both signal strength as well as noise strength. Let's come to the uncorrelated noise. The uncorrelated noise means, let us say your transmitter is turned off. Then you are trying to listen the corresponding signal from the transmitter. If it is turned off, signal strength is equal to 0. Whatever you are observing at the receiver end is nothing but noise. That means only noise is present here. Since there is no signal here, there is no relationship between noise and the signal in this case. That's why it is called uncorrelated noise. Again, this uncorrelated noise is categorized into two types. One is external noise, other one is internal noise. This external noise is nothing but, let us say if you have a system, if you get a disturbance in this communication system due to any external effect on the system, then it comes under external noise. The second case is the internal noise. Let us say you have a system and the noise is generated within the system while functioning is going on. Such type of noise we call it as internal noise. For example, the amplifier that you are going to use in a loudspeaker, if it is not functioning well, definitely you are going to get a noise at the output. And this generation of noise is due to functional behavior of the amplifier which is available within the system. That's why it comes under internal noise. Let us see what are the different sources of noise which are available. The first one is natural sources of noise. Second one is man-made noise. You can call this man-made noise as industrial noise also. Third one is fundamental noise. The other name for this fundamental noise is internal noise or internal source of noise. This fundamental noise is nothing but the internal noise that we have already categorized. Let us see all these sources one by one. The first one is natural sources of noise. The noise which is generated due to the natural phenomenon, we categorize them as natural sources of noise. Examples like electronic storms, solar flares, radiation from space, etc. will come under natural sources of noise. Once your communication system pick up any signal from these type of natural sources, there exists a noise which is developed in your communication system. If you want to overcome or else minimize this natural source of noise, the only option for you is to repositioning of antenna, or else you can change the orientation of the antenna, that is direction of the antenna. Since it is a natural source of noise, you cannot eliminate it, but you can minimize its effects by repositioning of antenna. There is one more term called extraterrestrial noise. The noise which is generated from space, we call it as extraterrestrial noise. If the noise is due to sun, then we call it as solar noise. If the noise is from any other part of the space other than sun, we call it as cosmic noise. Generally, that is the noise which is generated in stars. Scientists has observed that the noise from the sun will have a period also, and that period is around 11 years. That means the noise which is generated now is having a relationship between the noise which is generated 11 years back from now. Quasars. Quasar means noise originated from the center of our galaxy, that is Milky Way galaxy. The other type of noise is pulsars. Pulsars means noise originated from the center of other galaxies, that is other than Milky Way galaxy. These are all the different types of natural noises. Anyway, I already explained you, in order to overcome the natural noise or natural source of noise, the only way is to change the position of the antenna, that is repositioning of antenna. The second category is man-made noise. You can call it as industrial noise also. The industrial noise is generated by make and break process in current carrying circuit. Now, how do you define this make and break process in current carrying circuit? Let us say if you are watching a movie and all of a sudden a car driver ignited the engine, due to which you observed a disturbance in the picture tube of your TV, and this disturbance happened due to ignition of engine nearby the television, right? This type of noise is due to make and break process of current carrying conductor or current carrying circuit, and this is a man-made noise, right? That's why you call it as man-made noise. The same type of disturbance you will observe while changing the gears of a machine, or turning on or off of electrical motors, using of welding machines near to your communication system, etc. These are the different examples for man-made noise. The third one is fundamental source of noise or internal noise. As I already explained you, internal noise is the noise which is generated due to the functioning of the machine. Let us say you designed a rectifier, and this is the output of the rectifier. In practice, the output of the rectifier is something like this, that I am trying to represent in red color, and the value below this dotted line is nothing but cut-in voltage of the diode, which is nearly equal to 0.7 for silicon or 0.3 for germanium. In such a scenario, I can call the values below this 0.7 as noise, and this noise is internally generated in a rectifier due to the functional behavior of the diode. These type of noises follow some rules. If you design the circuit properly, you can reduce these type of noises, or in some cases you can even eliminate these type of noises also. Such type of noises we call it as internal noise. Since the cut-in voltage of the diode is the fundamental nature of the diode, due to which you are going to get this type of noise, we call these type of noises as fundamental sources of noise. Let me remind you one more example. Let us suppose you designed an amplifier, and an amplifier will have a parameter called S, which is stability factor. If the stability factor is good, then the output of the amplifier is good, that you already know. But you have different types of biasing techniques in your hand. One is fixed bias, collector to base bias, self bias. And you know that this self bias technique will give you the best stabilization factor when compared to above 2. If the stability factor is good, definitely the output will be good. Now if you have to design an amplifier, you will definitely use a self bias network instead of above 2 networks. As a result, you can reduce the noise which is developed internally due to the lack of stability. That means Proper designing will gives you good stability. Good stability will gives you less internal noise. So therefore I can conclude internal noise can be reduced by properly designing the circuit. Classification of noise. This classification comes under the category of fundamental sources of noise. That's why fundamental sources classification. Following are the different types of fundamental sources of noise. The first one is short noise. Second one, partition noise. Third one, low frequency noise. The other name is flicker noise. Fourth one, thermal noise, which is the most important one in all these types of noises. Fifth one is high frequency noise. Or transit noise. So the fundamental sources of noise is classified into these 5 types. Short noise. The short noise is generally observed in amplifiers. In order to explain this concept, I am going to take an NPN transistor which is connected in common base configuration. That means base emitter junction is in forward bias condition and base collector junction is in reverse bias condition. If emitter base junction is in forward biased and collector base junction is in reverse biased, this transistor will be available in active region. Now I can use this as an amplifier. During the operation of this transistor as an amplifier, the electron which is available at the emitter will tend to move towards the collector. For an instantaneous current which is given at the emitter, we expect that all the electrons will flow from emitter to collector instantaneously. But you know, the electron will not move in a straight path. It will move in a random path like this. Due to which the collector will not catch all the electrons at the same instant. Instead, the electrons are randomly collected at the collector end, and this effect is called short effect. If the electrons are randomly collected, definitely the current which is produced due to that random nature of electron movement will gives you a current fluctuation, and this current corresponds to a voltage fluctuation, and this fluctuation in voltage will lead to a noise, and that noise is called short noise. In a simpler way, a short noise is a noise where the electrons from the emitter will not reach the collector at the same instant. Instead, it will reach the collector randomly by generating a random current which will give rise to a random voltage, and that random voltage we call it as short noise. The short noise is exactly defined only for diodes, and the mean square noise current is given by IN square equal to 2 times of I plus 2IO into QB ampere square, where IN is mean square short noise current, I means DC current flowing across the junction, IO means reverse saturation current, Q is the charge, that is 1.6 into 10 power minus 19 coulombs, and B is effective noise bandwidth. We will talk about this effective noise bandwidth in a meanwhile, and this equation is applicable only for diode. The noise generated in any device other than diode will have only some approximation equations but not exact equations like diode. For an amplifier, the short noise is inversely proportional to transconductance of the device. and directly proportional to output current. That means as the output current increases, the noise will increase. Partition noise. This is due to partition of current. Let us say I have a connecting wire in a system and the current which is flowing up to here is only one. If I divide this current carrying conductor into two parts, then the total current which is available here will divide it into two parts, I1 and I2. During this process, the electrons which are available up to here, this point on the conductor, will randomly move in two different directions, due to which the partition of electrons will take place, and this partition is very random in nature. If the partition is random, definitely the current flowing in these two wires is also random in nature, which results in a random voltage or fluctuation in these two wires, and this type of noise we call it as partition noise. For example, if you take a diode will have only one conducting path. That means the partition noise in a diode is 0 or minimum. If you take a transistor, let us say the transistor is in common emitter configuration, the current which is available at the base is amplified at the collector. During this process, the current at the base node is divided in between collector as well as emitter. That means partition of current takes place. Hence this noise is called partition noise. If you compare bipolar junction transistor with a diode, a bipolar junction transistor will have more partition noise when compared to diode. Similarly, if you take a field effect transistor, the construction of field effect transistor is like this, right? And the current flow is from drain to source, or else source through drain, depending upon the biasing. In this case, the path is only one. As a result, the partition noise in a field effect transistor is less when compared to bipolar junction transistor. But there exists a gate current in this field effect transistor. If you can make that gate current as 0, definitely the partition noise in field effect transistor can be eliminated. In order to do that, devices like gallium arsenide field effect transistors are used. In a gallium arsenide field effect transistor, the gate current is minimized and it is almost negligible. As a result, the partition noise can be eliminated from your device. That's why in FETs noise is less when compared to BJT, that you have studied in your electronic devices and circuits. Low frequency noise or flicker noise. If you apply some DC voltage to a conductor, let us say I have a conductor here and I applied a DC voltage, and you know that the conductor has lot of charge carriers which are readily available, and those charge carriers are electrons. If I apply one voltage here, the electrons will tend to move in this direction. But the problem is the electrons in the conductor are not distributed uniformly. At some part, the electron crowd may be more, and at some other point, the electron crowd may be less. That means the conductivity offered by this conductor is not uniform throughout the length. And you know that as the charge carriers are more, the conductivity is more. Therefore, the conductivity at this point is more when compared to conductivity at this point. Even though the conducting wire is same, the conductivity offered by different parts of this conductor is different. If the conductivity is different, definitely the current flowing in this conductor is also different from one point to another point, and the multiplication of current with resistance at that point will gives you the voltage, and the voltage which is available across this conductor is also a fluctuating value. As a result, the voltage fluctuates in this conductor, which results in a noise called flicker noise. In a simple note, the flicker noise is due to non-uniform distribution of charge carriers in a conductor. And this phenomenon generally observed at low frequencies or else with DC currents. That's why this noise is called low frequency noise. This phenomenon is generally observed for the frequencies less than few kilohertz. That is why this noise is also called 1 by f noise. As the frequency increases, the value of this noise also decreases. That's why it is called low frequency noise. One more important observation is the mean square value of the flicker noise voltage is directly proportional to direct current flowing through the device. Which means as the DC current increases or DC voltage increases, the flicker noise is more. As the frequencies increases, the noise generated due to this flicker effect is less. So this is about low frequency noise or flicker noise. Thermal noise. I have taken a conductor and I placed it at room temperature TO. Due to the effect of temperature on this conductor, some of the electrons in the outermost layer will jump from valence band to conduction band, which results in conductivity of that material. The electrons are not distributed uniformly throughout this conductor. Even though I didn't apply any voltage here, since the concentration of electrons is more here when compared to this point, some electrons will tend to move towards in this direction in order to make uniform distribution. And this movement of electrons due to this concentration gradient is known as diffusion current. The current produced in this process is completely random and which generates a noise voltage, and this noise voltage only due to the effect of temperature, because here I am not going to apply any voltage to this conductor. That's why this noise is called thermal noise. If you observe the average voltage across this conductor, it is 0, because the current is flowing within this conductor, it is not going outside. But the average power is not equal to 0 in this case, which means there exists a power here, and that power is due to the temperature, and that's why it is called thermal noise. And this phenomenon is observed by a scientist whose name is Johnson. That's why thermal noise is also called Johnson noise. And this thermal noise is uniform throughout the frequency spectrum. As I told you, the average power is not equal to 0. We call this power as noise power, represented with Pn. N represents noise and P represents power. The noise power which is available in this conductor is equal to KTB, where K is Boltzmann constant, T is temperature in Kelvin, and B means bandwidth of noise spectrum. In a meanwhile, we shall see what is this bandwidth of noise spectrum. If you summarize this thermal noise is mainly due to the effect of temperature on a conductor, and there exists a non-zero average power. If I take a small circuit with a voltage source ES whose internal resistance is RS, if I connect this circuit to a load whose value is RL by using a conductor, there exists a thermal noise in this conductor which is not represented in the circuit. While you do calculations here, you are not going to represent that noise which is generated internally in this conductor. What we have to do now? We have to represent the noise which is available in this conductor also in this circuit. For that, I will use maximum power transfer theorem. In order to transfer maximum power from the source to the load, it has to satisfy the maximum power transfer theorem. And according to maximum power transfer theorem, the source resistance value must be equal to the load resistance. In such a case, the power delivered to the load, PL, max equal to ES square by 4RS or ES square by 4RL. If you apply the same rule for your conductor, the noise power which is generated in the conductor is equal to En square by 4R, where En is RMS noise voltage and R is resistance offered by the conductor. And the noise power that is developed here is nothing but KTB, right? That is equal to En square by 4R. Rewriting this equation, En equal to root over 4 KTBR, and this is RMS value of thermal noise voltage. In order to represent this RMS value and resistance within the circuit, either I can use Thevenin's theorem or Norton's theorem. These equations say that if we have a conductor whose resistance R, then it will generate a thermal noise voltage which is equal to En. And if you want to represent this noise in the circuit, then the equivalent circuit diagram is a resistance in series with an voltage source whose value is En equal to root over 4 KTBR with a series resistance value of R. And this resistance we call it as noise resistance and represented with R suffix N. And this voltage we call it as noise voltage or RMS noise voltage, which is represented with En. Therefore I can replace this R with R suffix small n. And this is voltage generator equivalent circuit. If you want to represent this circuit with noise, then the resultant circuit would be source part, noise part and load part. Sometimes you need to represent this noise part in terms of currents. In such a case, you will use source transformation technique, and by applying source transformation technique to this circuit, voltage source will be converted as current source, and the value of current is noise current, RMS noise current is equal to 4 KTB. Instead of resistance, now you will replace it with G, conductance, and this is noise conductance G suffix N. In shunt with a conductance whose value is 1 by RL, and this circuit is called current generator equivalent circuit for noise source, whereas this circuit is voltage generator equivalent circuit for noise source. Now you know how to represent the noise in terms of Thevenin's equivalent as well as Norton's equivalent circuit. High frequency noise or transit time noise. In order to know what is this transit time noise, first of all we have to see what is transit time effect. In order to explain this, I am using a small circuit here. It has a source of 5 volts 50 Hz, a PN junction diode followed by a resistance which is just a half wave rectifier. We know the operation of this half wave rectifier. For positive half cycle, output equal to input, and for negative half cycle, output equal to 0. If you talk the actual operation of this circuit, for positive half cycle, the electrons which are available in N-type material will tend to move towards P-type region. Once the voltage is greater than the barrier voltage, the electron will move towards P-type material. Similarly, the hole will move towards N-type material. Let us say an electron which is available here is moving towards P-type region into a hole. Let us say this is the length of the material, that is L. If the electron is moving with a velocity which is equal to v, Since I should not consider only one electron, I have to consider a bunch of electrons. I will use a term called Vg, that is the group velocity of the electrons. If you try to calculate the time taken for the electron to move from this point to this point on the diode, which is from n-type to p-type region, equal to distance L by velocity Vg. And this time period is nearly equal to some few nanoseconds. Let us say that value is 2 nanoseconds. That means the time taken for the electron to move from n-type region to p-type region, that means to overcome the barrier potential, is 2 nanoseconds. And if you try to compare the time period of the signal, that is f equal to 50 hertz, that implies time period t equal to 1 by 50, that is equal to 0.02 seconds. If you convert that into milliseconds, that is 20 milliseconds. If you compare t and tau, t equal to 20 milliseconds and tau equal to 2 nanoseconds. The time period for the electron to move from n-type to p-type region, tau, is very small when compared to time period of the signal. This is what happens at low frequencies. Instead of taking 5 volts 50 hertz, now I am going to consider 5 volts 1 gigahertz. That means I am going to use a very high frequency signal to the same circuit. Anyway, the time taken for the electron to move from n-type to p-type region, or from this point to this point, remains as it is, that is 2 nanoseconds, but the time period of the signal is now f equal to 1 gigahertz, right? That implies time period equal to 1 by 1 into 10 power 9, which is equal to 1 nanosecond. Now, the time period is equal to 1 nanosecond, whereas the time period for the electron to jump from n-type to p-type, tau equal to 2 nanoseconds. Tau is large when compared to t now. In this case, what actually happens is, by the time the electron will tend to move towards the p-type region, you are applying a negative voltage. As a result, the electron will tend to move towards in this direction. By the time this electron is moving towards to this right side, you are applying a positive voltage. As a result, the electron will move towards in this direction. As a result, the electron position will change, but the electron will never enter p-type region. As a result, even for positive half cycle or negative half cycle, the diode remains in off state. As a result, the output is 0 throughout the time period. But during this process, the movement of this electron in a random motion will give rise to you a small current, which is fluctuating current, which leads to a fluctuating voltage called noise voltage. The only thing between the operation in first case and second case is the frequency of operation. At low frequencies, this circuit is working as a rectifier, but at very high frequencies, the same circuit is not operating as a rectifier, only because of the time taken for the electron to move from n-type to p-type region. This time is called transit time, and this effect is called transit time effect. This phenomenon is observed at very high frequencies only. That's why it is called high frequency noise. The key point for this is, if the transit time is less than the time period of the signal, the circuit is acting like a half wave rectifier. But if the transmit time is greater than the time period of the signal, the circuit is not operating as we expected. And this type of noise, we call it as transit time noise.